what's up? Good to see you here, Matthew. Liking the intro right there. Some classic Smash Bros. Let me turn up the music right here. Where is that music button? Oh, there's the music dial right here. We got the Kahoot music now. We got the disco Kahoot music. It's my favorite. There's other good Kahoot music, like the 8-bit music. Where's the 8-bit? Oh, they got 16-bit, like SNES. I think we're going to switch it up right here. We got Radiant Meerkat. We're going to start here in about 2-3 minutes, so join in. Rapid Yeti. Let me see here, make sure I got everything the way it should be in the background. Join in. This code was on the screen a moment ago. Just wait a moment, then it'll be here. Okay. I like this. Everything good to go, it looks like. Here we're good to go. Re-show screen again. Here we go. Good to see you here, Bella and Sam. Matthew liking the intro. We got a few people, and we got 6 people in. Who's all going to be here? What do you guys think, guys, gals, pals? What do you think of the SNES music, the 16-bit music? I think it's a newer one. We'll put a 2-minute clock on. We'll get started. Now, what have we been doing online to help out? Has anyone watched the Discord? We've been doing something. I know Matthew's seen it. Parker's seen it. Matthew's seen it. What have I been doing twice a day? So we started doing it, I think, on Thursday. So you have Thursday, Friday, Saturday, Sunday, Monday, Tuesday. What have we been doing twice a day? I'm trying to do different ones each time, which I'll probably be able to do. It gives me 14 things. Practice interpretations. So give your own interpretations. There's no perfect interpretation. You can probably get 10 out of 10. I can still have critiques. So the goal is write your interpretations. See what you get or don't get, and I might add extra things to be like, oh, you should maybe add this, you should maybe phrase this differently. There's no perfect. I could give my interpretation to a statistician, and they'd be like, Brian, that's not perfect. Everyone's gonna have their own way of interpreting stuff. Good to see your Friendly Panda. Well, these are pretty. Oh, we lost Friendly Panda. Oh no, Friendly Panda's still here. We got the 2-minute clock on, so we'll get started here in 1 minute and 2 seconds, so 61 seconds now. Hey, Alex, good to see you here. So join in quickly because we're about to get started. We got Speedy Elephant there, looking like a. What is that? It's a lizard person with ice cream on their head. Interesting. Mubot's in the chat. Might throw out some Mubot points. You never know. We'll do 100 right now. Like 100. That's nothing, Brian. We got Giving Snail with those shades on. Like a unicorn with shades. Pretty cool. The brain with goggles on. Awesome Sea Lion. It's a... Oh my god. It's like a Einstein bear or something. Well, it's that time. I need some I'm raised in the chat. We only got about 20 seconds left. So let's put on our classic disco music here to start. We got to go to disco. Who's ready in the chat? It is time. We'll be covering a lot, so let's run it. So remember, ask questions, and there's going to be a lot of output in this. The Kahoot is one thing. You could probably ace the Kahoot, but you still need to know all the outputs. So we're going to stop. There's the bell. I'm going to stop with every output and make sure you understand it and can interpret it. So be focusing on that while we're doing the Kahoot. It's not just about answering the Kahoot questions right. It's about, and I do have randomized order of answers, right? Let me double check. When I make Kahoots, randomized order of answers, good. I have a way I make that I always put the answer in the top left, but the answers are randomized. Let's do this. 3, 2, 1. Here we go. Time for Kahoot. BAS 320 final review. 3, 2, 1. Here we go. First question is, if someone wants to predict views on YouTube, which model would they use? To predict the views on YouTube, how many views a channel gets? What model would they use? Now, really the last half of our class has had 2 types of models. Does anyone know in the chat the 2 types of models we've been using? What are the 2 types of models we've been using? And how do you know what type of model you're using? Hey, Aaron, good to see you here. So great job right there. A lot of people got this. Why is it linear regression? So you want to be able to answer why. Why is it linear regression? Linear and logistic. Good job, Emma, right there. Linear and logistic, which logistic does probabilities. So logistic models, linear models, and what's the difference between the 2 of them? Well, multiple just means multiple x's. The difference between, great job, Brian, right there. Really good job, everyone. Let's throw 1,000 points for all these right answers. What's the big difference between linear and logistic? Like, so multiple, you can do multiple linear, but what does linear versus logistic kind of differentiate between, which is a huge thing we have to know when you look at a model. Like, you should think, is it a linear model or logistic? Quantitative Y for linear and categorical for logistic. Perfect answers right there. Emma and Matthew, that's exactly it. So the way to identify the right thing to do right here is predicting views on YouTube is quantitative. So the views on YouTube are going to be a linear model. There are other models, like we could do neural nets, a lot of cool stuff. Yep, and usual just binomial logistic, 2 levels. Great answer, Sam, right there. And there is multinomial logistic. So you could do a multiple multinomial logistic, which is multiple x's, and a y that has more than 2 levels. I don't suggest doing multinomial logistic regression for your final. Make sure you have a 2-level categorical y of interest. Who's in the lead right here? Let's find out. Smiling urchin all the way up there. Oh, you got all those hearts above your head. That's cool. Awesome, Sea Lion. Great job, Clever Falcon, Dazzled Goose, and Rapid Yeti. Let's do the next question. Here we go. What is the typical miss the model makes? So might need to disappear. So look through the output here and find the typical miss the model makes. And this is a model predicting height from weight, I believe. No, I think it's predicting GPA. Look at the values. So the Y variable of interest was GPA. This is a simple quantitative model. Now, simple regression is the basis of what we're doing. You'll see more multiple regressions coming up later. But we should know all of this output, and we should know the typical miss the model makes, which is something we should probably interpret. Great job. Everyone knows that one instantaneously. It's the RMSE. So when you look at the values here, why is RMSE so important? It relates to what kind of, I don't want to say that. I'll see if you can get it. RMSE relates to the what of the model? RMSE relates to the, like, tell me a little bit more about RMSE. It's the typical miss the model makes. So the interpretation here would be when predicting GPA, we're typically off by about 0.6 when we make predictions. It relates to accuracy, what our typical miss is. And it's the it's error, a root mean squared error, and it deals with practical significance, like how useful is our model. So if we look at the average error or typical miss the model makes, like if I told you this, for a sports player, I can predict their season within about 30 of what they'll get. Is that good or bad? For a sports player, I'm usually off by only about 30 in my prediction for what they'll get for a season. So is that good or bad? 30 what? That's the great job, Ryan right there. 30 what? 30 running yards. When I make predictions, because I can look at a player and I'm usually off by about 30. Like, I'm not saying I will be off by about 30, but if you look on average, I usually am only off by about 30 for their running yards for the whole season. You'd be like, how in the world do you do that? But what if I'm typically off by predicting home runs by 30? That's close over 17 games. Well, yeah, that'd be insanely good, right? For running yards, because running yards is usually like couple hundred usually for people, or sometimes they do 1,000. But if I'm off by about 30 on average for home runs are usually in like the double digits, maybe 20, 30 if you're really good. So if I'm off by usually about 30, that's a big miss. Like, I predict this person's going to get 60 home runs and they get 30. And you're like, well, 60 is like record breaking, if I remember correctly, and 30 is really good. So they're not like the greatest of all time. They're just really good. And your prediction was way off. Like, I predict this player's going to get 60 home runs. If you predicted someone was going to get 60 home runs, it's a very high prediction. Is that the highest? It's like something in the 60s. Barry Bonds and Sammy Sosa, I think, were up there. So anyways, the context matters to this, and that's what we're talking about here, because once again, things like RMSE and R squared are used for what? Things like RMSE and R squared are used for RMSE and R squared are both used for what? We're talking about the full output right here, focusing on some big ideas for a moment. RMSE and R squared are both used for the what of a model? Well, for linear regression, that is correct, and for the what significance of a linear model. Well, R squared is the percent of variation we explain. Practical significance. Great job, Alex, right there. I'll throw 1,000 points. The practical significance. And these are all right answers. We're just like having a conversation. Like, they're all dealing with practical significance, like how good is our model? And then what is the deal with R squared adjusted? What is the deal with this metric over here, which we need for the multiple world? So although, and I guess that, it's pretty interesting right here. Well, I guess, that's interesting. Don't talk about that yet. But the R squared and the R squared adjusted, what do you immediately notice about them? it's a penalty for using more X's. And you know what's interesting? Even though this is the simple model, we do still get penalized. And you would say R squared adjusted is pretty good. Why? Why would you say R squared adjusted is pretty good? Usually what you can do with them, if you want to check it mathematically, is you take the R squared adjusted, and there's the R squared adjusted, and you do the following to see what you really got going on. And that's pretty good. So what am I looking at here and why? I'll zoom in on it so you can see. What am I looking at here and why? There's the math I just did. You can't see the other values. That's the R squared adjusted over the R squared. So by looking at the ratio of the two, you're seeing how far are they apart? And what do you want? Well, R squared adjusted is not, it doesn't have an interpretation. R squared is the variation in Y explained by the X's. That's R squared. R squared adjusted is after we penalize ourselves for adding in more X's. And Brian said it right, you want to be as close to 1 as possible because you don't want a huge penalty that all of a sudden your R squared adjusted is way lower. R squared will always go up. R squared adjusted can go down. And if the X's are bringing with it new information, they should stay relatively the same. Great answers, Matthew. Another 1,000 points. Yeah, that's about the idea behind it. And we can look at the p-values of the new X's to see which ones aren't really bringing with them new information. But the closer they are, generally you're seeing models with more X's bringing new information. The model is statistically significant. F statistics, the percent of variation we explain versus what we would have expected by a random chance. A ratio of that, 33 times more variation is explained than we would expect by a random chance. I don't know about interpreting that. Really, your highest value stuff right here is going to be the coefficient, the significance of the coefficient, the R squared, the RMSE, and probably mentioning that the R squared adjusted is good, and then the p-value. I did break up the output a little bit more on this test, giving you smaller bits of output in some cases. And I do want to say this. I did use a whole section of questions from the notes. Now, I want everyone to repeat that. A whole section of output is from the what's, like literally taken from it. There's a lot of things I could take from, right? But output literally taken from the notes. So if you know how to interpret output from the notes well, which we go over in class, should be pretty good right there. So that's a big up right there. It's a big good thing. Let's do the next question. Let's go to the leaderboard. Good review right there of that output. A lot of output to review right there. And Dazzled Goose is in the lead with Awesome Sea Lion right behind. Here we go with the next question. What is the misclassification rate of the model? So now we've gone over to Logistic. I'll zoom in right here so you can see it. Numbers are pretty big. I think you can be able to see it pretty well. Hopefully I calculated it correctly. What is usually the average for the funnel? I'm giving this funnel a new way. I do not know what it'll be. I hope it's probably, I want it to be around 80s or so. We'll see. I do not know. This is the first time I'm getting the funnel this way. Can't read the numbers? Make sure it's in HD. Make sure it's in HD. Only... Oh, no! I clicked the wrong box, everyone. I clicked the wrong box. We are going to restart the Kahoot really quickly. And let me do this. Who were 3 of the people who answered this correctly right here? Who was in the lead right before this? Dazzled Goose. Dazzled Goose, did you get that correct? Dazzled Goose, did you answer 17.7? Yeah, I did the classification right there. Oh, you Dazzled Goose. Who's Dazzled? If Dazzled Goose, you're the first person. I gotta fix that. If I don't fix it now, it's a problem. I don't know how I clicked the wrong button right there. Let me fix this. You ready? We're going to go let me show the output again and explain why I can't go back to it now. Let me show this. We're going to fix that. I'm going to take a screenshot of this. I'm Dazzled Goose. You didn't get it correct. Awesome Sea Line. Did you get it correct? I'm throwing you a $20 Amazon gift card for just saying you were Dazzled Goose and you didn't get it correct. So Sam, you've already won one $20 gift card right here. Alex, you did get it correct. So Alex, you're a winner too. You were in second. So we're going to I want to be fair. If I make, no, it's all right. We're gonna restart the Kahoot, go through those questions really quickly again. I'm gonna correct it right here. So you're gonna see this Kahoot end. Then wait, can I not? Here, wait. Sorry, we're gonna end it right here real quick. So you can't see the screen, but I'm just gonna end it. End the Kahoot. Is there not the ability to end the Kahoot anymore? What if I just leave it? I'm sorry, everybody. Oh, can I fix it? There's no way they let you fix things now. That's such a bummer. Okay. Let me fix this, everyone. How's everyone doing today, other than Brian making a mistake on the Kahoot? How is everyone doing? It might just... So leave that Kahoot. How's everyone doing in the chat? We're going to fix this up. So Alex and Sam, you are already $20 winners. Good to hear that, Matthew. A little chill music while we do this right here. What happens when Brian makes changes to Kahoots? And then we're going to talk about how to solve that. Second. Might edit. Doing well. Good job, Mitchell. Good to see you here. How could I do that? Okay. Save the Kahoot. I didn't change that to the right answer. Well, let's like change it. Okay. So now working on the project. Nice. Make sure your data is the right way, and that should be good. So leave that Kahoot. And then I'm going to go right back to the last question we were on. So give me 2 seconds right here. And I probably got to join in. 2 seconds. Oh, wait. Okay, well, if you remember the answers, there you go. So here's a good review for us right here. You ready? Joining the Kahoot, 1 minute on the clock. Joining the Kahoots, 1 minute on the clock. And we're going to get right back to that output. I'm going to explain how to find the answer. And if you remember how to do it. So 1 minute on the clock, joining the Kahoot. Leave that last Kahoot. Just X out of that page, throw it away on your phone. We're going to wait at least we got 5 or 6 in here because we had 7 last time. Joining the Kahoots. Remember, we already have 2 winners. The 2 winners we are saying are Dazzled Goose is a winner because these were the people who were in first who got it either right or wrong, and Awesome Sea Lion. So there we go right there, because they were in first. There was the wrong answer on there, so they would have they were in first, or they would have been in first. So good job. And so here we go. Let's join back in and let's do the coup. We got 10 people. That's good. All right, here we go. First question, answer quick. And we're not going to review too much, but, well, since we already have the answers for these. First question is, and let's remember how to do it. If we were predicting views on YouTube, what model would we use? If we were predicting views on YouTube, what model would we use? Nice and quick right here if you know the answer. Remember, views on YouTube are quantitative. We really only have logistic and linear models. There are other models like k-nearest neighbors, neural nets, discriminant analysis. You got it. It's linear. Ooh, people being quick right now. Look at that. 0.13 seconds are super fast. Next question is, what is the typical miss the model makes? I think everyone knows the typical miss is RMSE. I think everyone got this right last time. So great job knowing that RMSE is residual standard error. Just residual standard error. Oh no, sorry, person who misclicked. And now the next question is, remember we reviewed those. Woo! Ooh, was it the person who was quick who missed? What is the misclassification rate of the model? Okay, make sure you're in HD on the video. There is an HD button down below me right here. So you might need, there's a little scroll wheel, and that's easier to see some of the numbers. They should be pretty clear. Misclassification rate is found how? I know why, because I did the classification rate by accident. Misclassification rate is found how? So think about where we would misclassify things. Something is misclassified when. So understand what misclassification rate is. Great job right there. So things are misclassified. Like, what is an instance of something being misclassified? If something was what? Explain to me when something is misclassified. When is something misclassified? Like in this instance, predicted and great job, Ella, right there. Let's throw Ella. Great job. That is the exact answer. When the predicted and the actual are different, because, and Alex saying it right there too. So the misclassification rate is this right here, because you notice it doesn't line up. If you just trace across predicted no and actual no, predicted yes. So those are the misclassifications. So what is the mathematics right here? I'll start circling the numbers, but just think about how to do it right here as I sort of write it. And there's the total. So the mathematics is going to be the sum of things that are miscalculated, like how many are things miscalculated, and then over the total of how many things there are. So it'll be 2,310 plus 101 plus over 13,594. Now, there is one other thing interesting, which especially came up. Hey, Parker, good to see you here. Show the code here in a second. What's going on if I just look at this right here? I think a lot of people don't realize I'm just showing you the what values right now. If you only have this information, you're only seeing the what values. Just think about the only information you have. You're only seeing the what values right now. Kind of the observed, but the actual, right? The actual, right? Yeah, I guess observed. Brian, I got 30 points. That's usually we talk about in a chi-squared analysis. The actual, like what something actually is, or we observe it as, which is true, right? So what can you calculate from this or know from this? This is predicting if someone has diabetes, I think, or yeah, something like that. So this is predicting if someone will have diabetes. Good to see you, Courtney. So what is this? What is that going to tell you? Yes, no is the majority level. Now you have to be careful, and this is good stuff right here, because now we can figure out the what model from this. What model could you figure out from this since you know no is the majority level? What model would you know? Because most people don't have diabetes. You can figure out the naive. Now here's where I say you got to be careful. Because although no is the majority level, most people would be predicted not to have it, because if you just go by the basis of, do you think someone has diabetes? Well, most people don't have it, so you just think a random person doesn't have it. We would know that what in logistic is the what. What am I trying to tell you right here, which is not, and I mentioned this in the chat earlier, that is the that because it's that in logistic. So what am I trying to inform you of right there? Even though no is the majority level, it's the level of interest. The level of interest in logistic is last, but don't confuse that with the majority level, which is how the naive predicts. So lots of really good information, lots of good review right there. And you can see how the naive model predicts. The naive model doesn't have like predictions, so to say. It just uses what it actually is, the Y is. So you wouldn't need the X's in the model. So really good work right there. Let's see who's in the lead. Code's right down there. I'm going to pause for about 5 more seconds if you want to join in, anybody. And let's see who's in the leaderboard. Ooh, Mighty Yeti in the lead right there. Here we go with the next one. Let's do it. What does the output indicate? Oof. Oh my gosh. So you can see what that is. Okay. So look at the code, and then you should be able to see things pretty quickly. So then read the answers. There's what it is. I wish it was a little bit bigger. I took pretty big screenshots for this. Make sure it's in HD. What's the first things you noticed right here? Someone walk me through their process on this of thinking about it. So what's the first things you noticed? Like, what did you notice about this immediately? See, it's a little bigger there, I think, even. I'm pretty sure it is actually a little bit bigger. Come on, Coop. What are you doing about pictures? What do you notice about this? Like, what do you notice? And there's pretty much 2 things to notice right here. Matthew's saying it too. And the p-values are high. Boom. That's something we should notice immediately. High p-values. And then what analysis was done. So remember, p-values mean statistically significant or not significant. So we know this is not statistically significant. That's for certain. But that's not really what we're getting at with this, because what analysis was done over there at the top. And then I'm going to let's throw 1,000 points for these answers. Then I'm going to throw one more 1,000 points. Oh, you already answered my next question, Brian. Let's throw 2,000 points, because my next question was going to be, what kind of model did we make? And these are the checks created by these scientists right here, statisticians, to check logistic regression. So Brian already got to that next question I was going to ask, like, what kind of model was this for? And this is the check for a logistic regression. So logistic regression, to see how logistic regression is doing. So great job right there. Does it make sense that this was us checking to see, and can anyone give me a little more explanation? Like, once again, what would you say about this if you did this? Like, give me like a 1-2 sentence that you would probably write. Maybe you want to be thorough but concise, and this is kind of a yay moment if you see this after making an analysis. So what would your kind of shorthand analysis be? Like, you can go shorter than you might go on the test, but it should still be very accurate. And in a way in which people can understand it who don't know statistics. So what would you say? Like, think about how anybody who doesn't know statistics should get a general idea of what you're talking about. That's always what we want to do with our interpretations. And then we'll do the next question. So I put a lot of output on here. Remember, that's you could just get out. I mean, I'll tell you the truth. This is one of the possible 50 outputs you could get. There's like 50 outputs that you could get from, and there is an output picture of this. So the output we're going over right here literally is some of the output you could get. I didn't give you every single picture you could get. The notes of pictures you could get. We'll wait a moment more, see if anyone puts an interpretation. I'll give a little critique of it. I will give you 1,000 points for putting an interpretation, putting yourself out there. But try giving it a shot, giving a shorter interpretation of this to give like what you would say to a certain extent if this was on your test. Give it a shot. What do you think? I'll give 30 seconds until we move on. There we go. I like reading interpretations. Checking them all shows though to be appropriate for making predictions. The scientists who wrote the method 1, method 2 both agree that yes. And yeah, that's good. I might quote the p-values like truthfully to a reader. You might say both p-values show it's appropriate with them being above a 0.05, excuse me. So even I say 0.5 sometimes by accident. 0.05 by 0.05. This means for us that logistic regression is a good idea and it seems appropriate to use right here. So Matthew, great job right there. Another 1,000 points, Matthew. That's the kind of interpretations we're looking for right there. This is checking the appropriateness of using the idea of the model. So it's not really checking for statistical significance. It's saying, is the model appropriate? And that's our goal right there with this. Good job. Mighty Yeti in the lead. Swift Sloth and Wonder Llama. I like Legend Kitten. That's who I'm voting on. And Winged Squid. Next output is a multi-select. It might just be one. How many assumptions do we fail? You can actually... You can multi-select. You can multi-select right here. Why is the music not on? You can multi-select here. Oh my god. You can multi-select. And I'll explain why afterwards. The check regression shows that the model would be acceptable for making predictions, both in... Yeah, pretty much. So, when do we fail assumptions? When do we fail assumptions? When do we fail assumptions? When do we fail assumptions with check regression? When do we fail them? When do we fail them? When the p-value is below 0.05, exactly. So there's 1, 2, 3. But if you notice, there's kind of two answers right here. There's 3 as a right answer and 2 as a right answer. Why is it 2 but kind of 3 but kind of 2? Well, the p-value for weight is the p-value for the overall model because weight is the only x, so the linearity of weight is the same as the linearity check on the model. So really, you don't need to check. There's not 3 to check really because the model is the x variable, and this is in the simple world. Now, you do need to check the linearity of the model in the overall world, but overall right here, well, I guess I should ask this. What does this value right here mean? Like, go ahead and try to tell me what does that portion of the output mean? Like, write one sentence right there for that portion of the output. Like... without even seeing the graphics for it, what would that mean to you? And we really don't need to see the graphics at all. What would that portion of the output mean to you? Remember, the big thing to know right here, it's not about winning the Kahoot. It's about understanding all the output and being like, you know what that means. You don't want that to just be a number on your screen. You want it to be information you're receiving. What does that mean? What does that value mean? Not really that. That's the sample size. There were 699 observations used to create this model. Rows of data. Well, I mean, kind of, Parker. Yes. This equal spread. Pretty much. The equal spread p-value indicates to us that we do not have evidence of a problem. So remember, these p-values are to look for evidence of a problem. So I guess you could state that it's believable that there's not a problem, which you're doing right there. So I'd probably accept most, like, those are pretty good right there. I would say, you know, this would be my interpretation. I would say when we checked the equal spread, the test came back indicating there is not a problem via the high p-value. So, or like, if I'm not even going to mention p-values, I might say, we looked into issues of the different strength or different spread throughout the model, and we didn't find any issues. So this is saying you failed to reject the null. See, I'm not even saying that, because the null is that there are not issues. So yeah, as long, like generally like interpretations like that. The other ones come back with issues. Next question. Here we go. Let's do it. Ooh, leaderboard's tight. Mighty Yeti, Swift Sloth, Wonder Llama. Here we go. True or false? If we fail the test with p-values, we can't use the regression model. So if you fail these tests, you can't use the regression model. What do we do if we fail the test? Does anyone remember the trick if you fail the test? For 1,000 points, what do we do if we fail the test? Well, correct answers there is false. That is true. If you fail the test, you should immediately do what? Well, you could try good answers, Emma, right there. You could try transformations. That's a very Emma. I'm throwing you another 1,000 points. That's a very good answer. And Bella said transformations too. You could definitely try to transform for more linear relationships or to fix the residuals. You can try transformations, but if you fail the test, you should probably go look at the whats. If you fail the tests, you should probably go look at the whats. See if sample size is above 25, because if sample size is above 25, we can go look at the plots. So it's like we want to go look at the plots to see if the plots indicate there's big problems or small problems, because sometimes with large sample sizes, high statistical power, we learned about in 201, high statistical power may come into play, so we could find issues where there's very small issues. So if we see that there's a problem, we investigate further, and then we make decisions about using the model or not. So once again, you don't just throw away your model right away. You say, well, is it bad? How bad is it? Next question on the leaderboard. Go look at the plots. Yep. Great job, Courtney, right there. Mighty Yeti, Wonder Llama, and Dazzled Wombat on the leaderboard. Here we go with the next question. Which assumption can be checked using a QQ plot? Which assumption can be checked using a QQ plot? Well, let's see. QQ plot stands for quantile plot. It stands for matching up the quantiles of the normal with the quantile of your observed data. And it is normality. QQ plots for normality. So quantiles, it's looking at literally the quantiles matching up. And that's what the red line shows, is the quantiles matching up. So this is the plot to check for normality. And we do see some issues down here, probably due to some whats in the multiple sense. We probably have issues due to what's down here, even in the bivariate sense. Outliers. Yep, there's some outliers in the data, so definitely something going on right here. What do you use this first plot for? What is the first plot used for over here? Why do we use this first plot? Two reasons. Reason number one, reason number two. Linearity. The line is what I highlighted in yellow. So what you're seeing right there in yellow is the line. And if the line goes through the center of the data, the linear relationship is good. And then also what other issue too. This literally checks two issues. You can check for patterns, which would be what? We could see a pattern. We could see a pattern where the residuals start to do something like that. I do like that, Brian. Patterns is really good. Looking for patterns in the residuals. We don't want there to be any patterns. Equal spread. Emma said it right there. So equal spread. The spread of the residuals might change throughout the model. So we want to see if there's problems with it. And we can look at the residual plot to see that. So is the equal spread good? How are we looking at that? And yep. Next question. Here we go. Mighty Yeti, Wonder Llama, and Legend Kitten. This is a tight game. Next question. Which level has the strongest relationship? Let's see what people say. No, I wish I weighed less is the black line. No, I wish I'd weighed more is the red line. And yes is the green line. Yep. And what are you looking for right here? The strongest relationship is found by looking at the what? How would you know the strongest relationship? How would you know the strongest relationship? The slope, the steepest line. And so what kind of model is this? Does anyone know what kind of model we're looking at right here? This is a model we did about a month ago. What kind of model is this? For 1,000 points, what 2 things does this model have in it? What kind of, it's a multiple linear. Like that, I'll throw 1,000 for that. It's multiple linear. And what are the X's? Yeah, that's the Y. It's a multiple linear regression. And what are the X's now? Indicators. It has indicators. And then there's a what with the indicators. So you can see the indicators right here. Good job reviewing. It's indicator regression, but then indicator regression creates an MSA right there. There's an interaction. The interaction changes the what's. The interactions allows for differences in the what's between the lines. The interactions allows for differences in the what's between the lines. And really good review right here. This is a multiple linear regression with an indicator X having an interaction between the quantitative X, and the interaction is allowing for the different what's. Because if you don't have an interaction, the lines will be parallel. That gives it away a little bit. The interaction is allowing for differences between the what's. Because it's interacting on the quantitative X, slope, great job, Ella right there. Or Bella, sorry, Bella. Yes, exactly. Does that make sense right here? So try making models like this. Like, does anyone who thinks they could make this model using, I think I used Survey 11. Does anyone think they could go into Survey 11 right now, use these variables, and make this same model? Which is something I'd really, I don't know, if you want to try and make it and interpret it, give it a shot. But you can see the names of the X's right up there. You can see the Y was height. And so, yeah, you can try making it and then interpret it. Good practice right there. And then look at the coefficients. So once again, you could get output like this on the screen. If I were to interpret this, I'd write something like a multiple linear regression was made using a quantitative variable weight to predict height, and also the categorical variable if people are satisfied with their weight, which has 3 levels. Boom, 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 boom. The strongest relationship was with yes, which has the steepest slope, and the weakest relationship was with no, I wish I'd weighed more. Yeah, because you can kind of tell the black line's catching up to it. I don't know, you could probably write a little bit more, but thinking about the most important things first, telling someone what this model is, and, you know, you could say maybe there's maybe some strong outliers, but there might be some problems with this, especially. I don't know. Not a ton to say for this one. 2 or 3 sentences would be good, but making sure people know what it is, what was created for them, and understanding kind of what are the X's and what are the Y's. So good stuff right there. Let's go on to the next question. Ooh, Swift Sloth jumping up there a little bit. Next question. Multiple select. Multicollinearity. What about multicollinearity here? Okay. Multicollinearity. And you got a really cool picture on here. I think this is via the, what is it, from the psych package or the, I don't think which package I made this from. But what is it showing you? You've got the cars data right here, and you've got a bivariate relationship. Good job. Very happy with those answers. So how do we check multicollinearity first off? How do we check multicollinearity? How do we check it? What code do we write? VIF, variance inflation factor. And what do you want your variance inflation factors to be? Hint for a question coming up. What do you want your variance inflation factors to be? Now, it doesn't invalidate a model. It's shared variation in your X's. You want them to be as close to 1 as possible, and that would mean, think of an I word, your X's are what of each other. If they're close to 1, that means your X's are really what of each other. Think of an I word. It means they don't have their variation explained by each other. They're really what of each other. Independent. Great job, Hayden, right there. Excellent work. Hayden, I think you're visiting, right? Ooh, are you here visiting, practicing? I think so, right? I'm trying to remember. So many names for me to remember, and I think Hayden's visiting practice. Is that right, Hayden? We're going to throw some 5,000 points. Shout out to Hayden right there. No, Hayden, you're this. What am I saying? My brain. Too little coffee. I'm on my 2nd cup, and I need more. So, no, really good work right there, Hayden. They're independent, and that's kind of what you want. Because what happens, like, what's the problem with variance inflation factor? What's the problem with the variance inflation factor? Because variances really are what? what is the problem with inflating the variance? Variance is really what squared, which we don't want that to be bigger because that's confusion, or that is our uncertainty. So variance is really what? You don't want there to be shared variation in your x's because your x's are then bringing the same information. Then your model gets confused, and the variance is not where we see it. It is variance, but we see it with an increase to the what in the model, in the parameter estimates. Variance squared, or excuse me, this squared is variance. So if you square root the variance, you actually get an estimate of the blank. Here's a hint, SE. Not quite standard deviation, standard errors. Good job, Sam, right there. The standard errors for the estimates of the parameters, which are the uncertainty amounts. So those go to create confidence intervals and go to create p-values. You don't want large standard errors because large standard errors are a metric of uncertainty in your variable estimate. And when you have large standard errors, it's bad. So we don't want our x's to step on each other's toes. We want the variance inflation to be close to 1. So let's take a look at an upcoming question right here. Good work. Mighty Yeti still in the lead. Okay, next question. What do the VIFs indicate? What do the VIFs indicate? Kind of reviewed it a moment ago. Remember, I can only write so much in the Kahoot, so these are not meant to be full answers. Good work right there. And so let's pause and see, what would you write for this? If you had to write 2 to 3 sentences for this, what would you write? So take a moment right now, like it's the test, and write 2 to 3 sentences. Write 2 to 3 sentences. I think you can write 2 to 3 very powerful sentences about this output, explaining to someone what it means. It can be done in 2. You could always throw in a third to make it a little more powerful. Take a moment right here to practice. Once again, this is one of the many outputs you could see on the test. And all it would be is with different x's. That's a hint for how I would interpret it. So try to give this a good interpretation right here. Once again, there's many, many outputs you could see on the final. All the outputs are just from the notes or from things we've done. Or I've created some new ones, but there's a lot from the notes. You'll see, you'll be like, oh my God, that was in the notes. So if you know someone said, this output I got on the test and it was in the notes, well, technically any of them could be. And it's selected from a pool of 50 questions, which you get 10. So there's a lot of randomization to what you could get. So everyone's test will be pretty unique. So try to interpret this right here. Remember, we give 10 points for some stellar interpretations, 9 for really great, 8 if it's got some problems, 7 bit more problems, 5 it's really lacking, 3 it's got something good, 1 there's something in there that means something. So how would you interpret this? How would we interpret this? I'll give it another 30 seconds and we'll go on to the next question here. Which GPA and Greek life bring in new information? Careful, Matthew. I'm glad I said this. So VIF does not measure new variation. VIF does not measure new information. That's found in the what of the X variable. VIF does not measure new information being brought. So VIF does not measure new information. New information is only measured in the what of a variable in the model. To see if a variable brings new significant information, that would only be measured in the what. Now, because I kind of get what you're saying a little bit with new, but like, I might give that like an 8, because when we say new information, we're usually talking about the Y, and that deals more with the p-value in the summary. This would mean they are bringing unique information. So you could change new to unique information. Now, so small difference, and that's why I'm like, it's an 8 or 9, I'm thinking. So what we have right here, And so, yeah, so usually when we say new information, we're talking about the p-value in a summary. So I'm like, I kind of see what you're getting at. I guess maybe my stats mine's a little too much statty. I think the thing to mention here is, I think Brian's word of unique is good or non-redundant. Like unique would be better right here to say the 3 X's, blank, 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 weight, GPA, Greek life, all bring with them unique information as seen by the low VIFs. The lowest a VIF can be is 1, which would mean the variables are completely independent and all have unique information with no overlap. These values are so close to 1 that the standard errors are going to be virtually unchanged by the overlapping information they bring, which is close to 0. The VIF checks for multicollinearity. The value is close to 1 means that correct. And then Sam, you got to give it, and then Sam, good work right there. That is good information on VIF. And then make sure to then give the context for these, like to mention the variables by name. So remember, whenever you're, that's the thing is, so Petrie has a good way of talking about this. If you Google it, it will say 5 or 10 because it's like, so basically, what's the thing, Brian? What are VIFs are bad? Yeah, exactly, Sam. So what are VIFs are bad? So finish that sentence. What are VIFs are bad? Higher VIFs are bad. The larger the VIF, the worse it is. And so if your VIF is 4, your standard errors are about how much larger. If your VIF is 4, then your standard errors are probably increased by a factor of what? If they're 4, if your VIF is 4 for something, then the uncertainty in that variable is probably increased by a factor of what? Remember, VIF is standard error squared. Well, not 4 times, that's the variance. So the standard error has been increased by a factor of what? The standard error by 2 because it's square root of 4 because variance is standard error squared. So if it's 9, then you've increased your standard error by about how much? Like if you have a VIF of 9, then your standard error, your uncertainty is about how much larger, like you have how much more uncertainty. It would literally look like this. This is your uncertainty confidence interval, and then it would go like that. That'd be, which if you saw what I did, if it's 9, your standard errors have been increased by a factor of how much about? Once again, its variance is square root it and you get standard error. So 3. Does that make sense mathematically? So a lot of things online will say 5 or 10. There's another way to look at it that you can look at how much your model does. And if your model has a really high R squared, then your X's might have overlaps. Great job coordinating right there. I'll throw 1,000 points. So the more R squared you have, the higher the variation explained, the more possibility for your X's to overlap, and usually the more forgiving we are. Does variance inflation invalidate models? Does variance inflation invalidate models? Yes or no? Does it invalidate models? No. It's just going to make it harder for your X's to kind of be what in the model? Think you have more uncertainty, which means your intervals are going to be wider, which means they could contain 0. It's going to make it harder for your X's to be what when they have so much overlap, when you're like, I don't know how to use this. So when you have variance inflation, multicollinearity, more uncertainty, it's going to be a lot harder for your X's to be what? When you have so much uncertainty, it's going to be a lot harder for your X's to be what? So it's not a good thing. We don't like it. Here's a hint. The T ratio is the estimate divided by the standard error. So you have your estimate and standard error. If you divide the estimate by the standard error gets bigger, the T ratio gets smaller. And if the T ratio gets smaller, the what gets bigger. If the T ratio gets smaller and the T is closer to 0 at the center of the T curve, so if the T is closer to 0, your what is bigger? So a T closer to 0 will make a what bigger? Which is the last part of the p-value. Yep. So when you have more uncertainty, it's harder to get what? So think about that then. If you have more uncertainty in how to use an X, it's harder for that X to be what? Which is what variance inflation is. It's inflating your uncertainty because variance is standard error squared. So it's harder for the X to be what? 2 words. Once I say 2 words, I think someone knows exactly what I'm talking about. With higher variance inflation, it's harder to get X's that are what? Boom, Emily right there. Statistically significant. Great job. Exactly. With higher variance inflation, it's hard to get X's that are statistically significant. So we don't like it. It's really bad for models. But I mean, it's not the end. Depends on how bad it is. We look at it. Mighty Yeti in the lead. Good to see you here, Emily. Swift Sloth and Wonder Llama. Let's do the next question. Here we go. What does the p-value for the interaction mean? Ooh, bet people are going to get this right here. What does it mean? And go for the best explanation. What does it mean? So in the multiple world, it's very important to know what the interactions mean. Wow. So yeah, I think I noticed it. I'm like, I think I assumed because I was looking at this. Yep. Come on, Brian. Don't get a second question wrong, Brian. Don't do it. Ah. So what did you look at right here? The p-value is what? The p-value is below 0.05. Does everyone see that? And then the multiple world, when p-values are below 0.05, it means it brings new information. So to know if something is bringing new information, does anyone know what code I ran to get this? There's probably two codes I could run. What do we usually run to get this output right here? What code was ran for 1,000 points right here to get this output? That's a what of the model. Summary. Great job, Brian, right there. So that's a summary. Great job, Emma, there too. That's a summary of the model, and the p-value being low means that it brings with it new information. And probably, why do you think that weight is not significant in predicting someone's height? Does anyone have a guess why weight might not be significant? I could probably remake this model and show you. Let's show that right here. 04, 78, and interaction between 04. Okay, let's go show that. I think. Okay, so data, library, reg class, data, survey 11, attach, survey 11, and now I already attached it one time. M save into LM X04. Wait, we're predicting height, right? Where's height? Hey, well, good to see you here. Oops. X04. And then where was the interaction? 4 and 7 have an interaction, then 8's in the model. Okay, 4 and 7 have an interaction, and then 8 is in the model. And you don't actually have to do data equals because it's attached. Not the best way to write your stuff, but still. Some codes won't work properly. So there's the model right there that we see with the high p-value, or the low p-value, excuse me. And the problem with it, why do you think weight is not significant? For 1,000 points, does anyone know why weight is probably not significant? And I'll show you something. Let's remove this. And I bet you weight is significant. So why do you think weight all of a sudden becomes not significant? Literally, it's a review of what we just talked about. So there's without the interaction. Here's with the interaction. And why is weight probably not significant right now? Think of what the interaction is built from. The interaction is built from the variables. So the reason that weight is probably no longer significant is that and that. They're doing what? They bring what? Greek life is the only one bringing what? So this is why weight is no longer significant, which is what we just kind of talked about with this. It's funny that. So what's going on right here with this model? Which is not bad. It's just what happens when you make interactions. Because the interactions are made from the variables. The interaction is bringing a lot of the what's. How did I just create a point worth class? Is there... Nope, I put it in. So what's going on down there at the bottom? The interaction right here, Parker, is bringing new information to the model. The height, weight, or the height GPA interaction is bringing new information to the model, but the interaction has redundant information with the other variables, it looks like. There's redundant information in the X's, but the one that's bringing new useful information to the model now, which is seen up here, is that the interaction is bringing new useful information to the model. We can see here in the simple world, you're welcome, Will. So the simple world shows that weight is significant and GPA doesn't bring new information. Greek life, yes, does not bring new information. Weight does bring new information. Down here, GPA is bringing new information to the model, significant information. This one is not bringing new information. This one is not bringing new information. And right here, we see that the interaction is bringing with it new information. But probably the issue is, no worries. Well, good job right there, Parker. Is this, who feels like, get a yes, put a yes or no in the chat. Does anyone feel like they understand VIFs right now, especially and what the VIFs are showing us? That the VIF is a measure of the redundancy in the information of the X's, and that's probably what's creating the issue right here, that weight is no longer significant in this model, because before including the interaction, there really wasn't a redundancy, and now including the interaction, there is a redundancy, and we could check this by going back here, removing it, and there's no redundancy, and now you can see, I think I'm confused. When do we look at the direction of the estimate again versus looking at the p-value? The direction of the estimate right there will tell us the nature of the relationship, that this is saying at higher levels of weight, and we can look at a model really here quick with that. Let's go reduce this model down a little bit so we can see it. At higher levels of weight, let's see if it stayed the same. It is positive. Okay, so weight and GPA have negative coefficients. Does that make sense? Weight and GPA... Correct, Sam. Even if something has a, then, so it can be, to Sam's question right there, VIFs measure the redundancy, but something can still bring new information and have high redundancy. So, pretty interesting, right? So it's two different things. You have to separate the idea of new information, which is this, and you have to look at you have to separate redundancy, which is this. So something could be very redundant, but have in it new information that's valuable. It's where you have to think of it as two separate ideas. And let's go look at this to Bella's question right there. We're going to visualize this, but let's think about how it should look before we visualize it. Let's say somebody has a GPA close to 0. So in that instance right there, we would not change the coefficient of weight. Does that make sense? So if you plug in here a GPA of 0, then it would not change the coefficient of weight. But when somebody has a higher GPA, the coefficient of weight will become more what? When somebody has a higher GPA, the coefficient of weight will become what? Or go more what? For higher levels of GPA, the coefficient of weight will become more what? So we need to look at the sign right here. For higher levels of GPA, the coefficient of weight will become what? Right now, weight has a negative coefficient. It'll go more positive. So let's look at the, I think it'll do if we visualize it. There it is. Okay, I really like this one over here on the right. So here it is. For higher levels of weight, the coefficient of GPA is more positive, because the coefficient of GPA is what to begin with. The coefficient of GPA is what to begin with. The coefficient of GPA is what to begin with. What is it to begin with? You can just kind of state to start. It's negative, right? So you see the blue line down here. So for lower levels of weight, we're not going to see the interaction making it positive yet. So for higher levels of weight, when weight is higher, the coefficient of GPA will be higher. Does that make more sense to see it over here, Bella? Like when you look at this graphic, this one's a little bit harder to see it with, but it still works the same way. That for lower levels of GPA, the coefficient of weight will be lower. For higher levels of GPA, the coefficient of weight will be higher. Yep, and then just think about what this means, that you're viewing the interaction right here and then talking through it like that. If you see, and I will say it, I did put a plot like this. I do know the plots I made, and I did take a plot like this showing the implicit lines, talking about interactions right here. So you might see a plot that looks very much like this. So good questions right there, and think about how to talk about them and what they mean. Okay, next question. Leaderboard. Woof, we got a big leader right here. Mighty Yeti in the lead. Next question is multi-select. What does the following show? Why did I select multiples on this? Oh no, there might be one wrong answer in here that's selected as a right answer. What have I done? What have I done? Pretty sure there's just one right answer, but I must have clicked 2 by accident. Or did I select them all? Because I was changing answers in here. This is something we did at the very end of the semester here, so I hope people aren't forgetting it. I think I have 2 answers by accident. It wasn't a multi-select. Good. Well, I was like, why does it say 2 answers? Okay. I think it was previously. Okay. So with this right here, it was a trick multi-select. So this is the start of a step procedure, because what can you tell? If you know the code right here, what is this showing you? What is this showing you right here? What would you write on this? I think a lot of people might have no idea what to write on this, but you could write two, three strong sentences pretty quickly. So what could you write on this? What could you write? And I probably want to disappear so you can see the values over here. So what would you write on this? What could you write? Try writing this. Remember, there are pictures like this on the test. So you have to know what this is showing you. No worries. Give it a shot. So what is a step procedure? What do we use the step procedure for? The step procedure is used to figure out the variables in a model, so you can do model selection on your assignment. If you're doing the project, you can use the step procedure to do model selection for you, variable selection. So you can do step. That's an option. A lot of people are having issues with build model, so try that out maybe. So the step procedure right here is looking at including variables. I don't want to say too much. I want to see people right. We're starting with this. We're going up to that, which is all the variables. We're going into this direction to review the step procedure 1. Put a lot of stuff on here that I want to make sure people know. Remember, it's all about that output. If the output is in the notes, it could be on the test. I'll give it another 30 seconds or so. Remember, you want to tell people what this means if they're not in statistics. What does this mean? What's the point of it? What are we doing? Why are we doing this? I'll give my interpretation in 30 seconds. Give it a shot. Don't worry about getting it wrong. Definitely, if you want to try doing the step procedure for your project, it'll help too. This was, I think, Thursday last week, or the week before. I guess still last week before. Okay, we're getting close to 30 seconds, and I'll give my interpretation. The step procedure is looking at which variables to include. Gender has a lower AIC of this, so might be the X variables to select over weight, which has a slightly higher AIC. Yeah, it's pretty good, right? That's pretty good. So that might be, I think, and that's why I put stuff like this. That might be an 8 or 9 right now. So I would say, I like the start right there. The step procedure is looking at which variables to include in the model by adding them into the model. That's the forward method right here, to add variables in. We have started with the naive model. Does everyone see right here where it says height ~1? So that is the code saying starting for the naive. Does that make sense? So we have started with the naive model, and we're looking at possibly adding in two variables, gender and weight. The variable that will be added when we take our first step forward will be gender, because gender has the lowest AIC, and lowering the AIC brings us closer to the truth. The step procedure will then consider each variable after this, and if you said that right there, you'd get 10 out of 10. But I'll repeat it one more time right here, how I would interpret this for a 10 out of 10, and I'll give you kind of the necessary components. 1, you need to talk about the step procedure being how we choose variables included into the model. So we're looking at selecting variables and putting them in a model, starting with the naive, going forward by adding variables, going all the way up to a model that is complex, which is probably all the variables in the model. We are currently at the naive model. This is the current where it's at, and we are considering XO2 and XO4. The reason gender will be selected, XO2, is because it has the lowest AIC, and that's how we choose to add things into the model. And that's probably enough right there. Does that make sense? Who understands my interpretation right there? And that's kind of the important part. Remember, read over the notes again, watch the videos again. We go through output. I think I took this directly in. No, I made this one. But I did take ones from the notes. That's some hints right there. But you should have some strong sentences for each of these, explaining to someone what's going on, that we're just looking at figuring out what variables to add into a model. We're starting with no X's in the model, and then we're adding in the X's as we go via what's called a forward procedure. And the forward procedure is going to start with the naive here this time, which is no variables. Kind of repeating myself. But think of some strong sentences as you write them right there. Very important. Remember, we did go through model building, so don't forget to review those notes. Oh, it's a close game. Mighty Yeti still in the lead. Let's find out who's going to win. Which way do we interpret height? Ooh. I like this one. You got to look very carefully at the output. Look very carefully at the output. What's the first thing to notice in the output? What is the first thing to notice? This is huge right here, and I thought this one might get people. What's the first thing to notice? The first thing to notice. GLM. Emma, did you get it? Categorical Y. So we're predicting probability right here. So it's all, so I think they got it right there. This is a tougher one. So when you think about this, it's predicting probability someone's male. And so we don't want to say height increases gender or gender increases height. We don't go with that right there. We're talking about the probability that the positive coefficient right here would increase the probability someone is male. So when we have two people, the person who is taller is more likely to be male. It doesn't mean they are. It just means they're more likely. Just looking at data. So that right there, and it's not one unit differences, but good work. This was a trickier one, but we don't like to say that one variable increases another. It's kind of cause and effect relationshipy. But if I were to just interpret this coefficient, I would say that I think 3 strong sentences are probably good. You don't want to go too crazy. Like, the stronger your sentences are, the less of them you need. So don't go for like huge paragraphs, because if you start to put too much fluff, it might start to decrease. And the test kind of says that like, go for like concise. I could show you it. I wrote like, make sure to be thorough, but be concise. And that was like, these are things in conflict. So it's something I work on with myself, being like concise, but thorough. So it's really tough. But I'll be nice, but if you start going too statistically, or if you start being like, the p-value of less than 2 to the e to the negative 16 indicates that the z-score was calculated by finding don't worry about telling me about the z-score. Probably even the standard error, not so much, unless I just show you standard errors, which are amounts of uncertainty in the estimate of coefficient. So yeah, go for the biggest things first. And the biggest things in this output would be, frankly, the coefficient of height. In this output, that's about the only thing that matters. Here's my 2 to 3 sentences on this output. A logistic regression was made to predict the probability of gender, where the level of interest was male. I probably would tell you that in the thing. The level of interest was male, using the x variable height to explain it. The x variable height has a positive coefficient, indicating to us that two people where one is taller than the other, the person who is taller has a higher probability of being male. And this variable does bring new information as shown by the p-value. Does that make sense? I think I got 3 sentences right there. I kind of mentioned what the model was. I mentioned the coefficient. I mentioned the p-values, the p-value that it brings new information. So told you what the model was, told you what the coefficient meant, and told you could do a ratio. The only other last thing, which I would think could be of somewhat importance, is taking this right here. And what am I currently finding? For 1,000 points, does anyone know what I am finding right now? Which is maybe the only last thing to find. So we are using height. What did that's probably a pretty, I'd be actually very impressed if you found that and you calculated that for me right there. I would be impressed. If you calculated that, I'd be like, and then you told me what that meant. Because we're not just going to calculate that. What does that value mean right there? Any ideas? So I took the negative, I did negative B0 over B1. What does that value mean? And how would we tell someone what it means? So it's one thing to know what it means, and another thing to tell somebody. I'll interpret it in like 20 seconds. So once again, I did negative B0 over B1. And that value means at 69 inches, or 68.5, is the point at which someone would have a higher than 50% probability of being male. So this is the point at which we would predict somebody is male. So if somebody's 68.5 or taller, they would be predicted to be male. Like, that's the more likely scenario. Does that make sense? This is the 50-50 breakpoint on the logistic curve. As the logistic curve goes up, and once again, I wouldn't write all 3 sentences. My sentence on this would be the point at which people are predicted to be male is after 68.42 inches. People taller than that would be predicted to be male. Does that make sense? That's probably the last thing. So I had 4 things, and that would be, frankly, if you got that last thing, I'd be very impressed. Then I'd look at that and be like 10 out of 10. I would just like immediately give it a 10 out of 10. Without it, I'd be like, that's 10 out of 10. So not looking for perfect with 10 out of 10s. I'm looking for very super strong, though. I'm looking for like, you have 3 sentences that are like Good stuff, good stuff, good stuff. And then if you wow me with another sentence that's like another one, I'll be like, whoa. So here we go with the next question. Let's do it. Multi-select. All these multi-selects it may or may not be. Which of the following are true about R squared? This is a multi-select. This is a multi-select. Reviewing R squared, going back in time a little bit here, this is a multi-select. This is a multi-select. And I better not have selected them all. So when you think about it, R squared is a penalized R squared. What's the lowest R squared can be? What is the lowest R squared can be? What is the lowest value of R squared, which is the percent of variation Y explained by X? So if you know that it's a penalized R squared, what is the lowest value R squared can be? The lowest R squared can be is what? 0. So that means very clearly if it's a penalized R squared, that means what? If it's a penalized R squared, that means very clearly what? If R squared can be 0, R squared adjusted can be what? If it's a penalized R squared and R squared can be 0, it can be negative. And then also think about this. What's the highest value of R squared? So what is the highest? Like R squared can only go up to what? What is the absolute highest value of R squared? 1. So can R squared adjusted be over 1? No, because it's R squared with a penalty, and if the highest R squared can be is 1, then R squared adjusted can't be over 1. We do use it to compare models because it puts models on an even playing field, so models with more variables get more penalty, and it evenly compares models. Mighty Yeti, oh no, dethroned by Wonder Llama. Here we go with the next question. Let's do it. Someone creates a regression using months of the year. How many indicators will there be? Well, I like this one nice and quick here. How do you figure out indicators? Indicators are for categorical X's. So how do we figure out how many indicators there are? How do you figure out how many indicators there are? Blank minus blank. So the amount of indicators is very clearly blank minus blank. Yep, levels minus 1, or levels minus 1, levels minus 1. And technically it's called in notation K minus 1, K being the amount of levels, 1 being subtracting. And where does that 1 go? That 1 goes to the where. That 1 is for the what. So the 1 is for the what level. So we have indicators and we have a what level. And you don't see it in the output because it's, well, the indicators are what we see. The reference, the reference level. The reference is what you don't see. It's not in the output, and so it doesn't have a level to it. So good work right there. The reference level. Yep. God, maybe I think we have 1 or 2 more outputs. Ooh, it's a close game between Wonder Llama and Mighty Yeti. 2 more questions to go. Which order should we use? Yes. I think you can see it pretty well. Yeah. Only not too much to look for. I maybe should have made... No, the answer's pretty clear with what I put. What are people looking at to figure this answer out? Yeah, I could have made it a lot. Yeah, no, the answer's still that. Either which way you do it, there's an obvious answer to this. Oh, a lot of people said 6. Okay, so what should you look at to figure out the answer here? What should you look at to figure out the answer here? And what would be this output? Choose order looks at the polynomial order for a regression, AIC. Yep, and AICC is, it's AIC basically. AICC is Akai-Ike's corrected criteria, the information criteria corrected. It just has an additional penalty term, so it's basically AIC. And so when is AIC better? This one's pretty obvious on which one to use. AIC is better when AIC is water. AIC is better when AIC is water. Now, you might be looking at your R squared adjusted, but I'd probably look at the AICs. Probably look at the AICs. Lower. Someone could theoretically make an argument for 6 because they might have just gone by R squared adjusted, but preferably, now what argument would you make against them, which is the argument I would make against them right here. So what argument would you make against them right here? And you could just do some quick math. I would argue against them using this metric right here. And then, so this will be the conversation we had. Significant differences in the AIC because they're more than what? It's kind of in that gray zone, actually. Because remember, we said, so think of some numbers we talked about with the AIC differences. That's why you're seeing maybe some little bit of confusion here and here. This is where you probably want to do some write-up on it. So what are the differences in the AIC, and is that a big difference? AIC does not have an interpretation. It is said to be how close we are to the truth, but it doesn't have like a mathematical like units to it. The lowest AIC can be as negative infinity. These are just facts about AIC. So I would calculate the difference right here. The difference is 7, right? Why am I looking at model 6? Why is model 6 of interest to me? Now, this is a polynomial order. I'll show you what this looks like. I can't remember what model I made this from. Let's go over here. That might have been something like this. Or actually, I think it's the weight. I think I used weight. That is it. So what are we trying to find right here? What are we trying to find? What's the point of this code? You might start with that. That's a really good place to start. Like, what are we doing? So what are we trying to do with choose order? So this is your goal with the test. Is like, explain what's going on here and what does it mean and what do you decide? What is the importance? Because it's not about running the code. It's knowing what it means. So we are looking at the inclusion of polynomial terms in a model, and this wasn't provided to you. We could give the context now. We could say height being explained by weight. So we're looking at possibly allowing the model to have more like bends throughout. Like it's no longer going to be a line. It's going to have some bendable ability. As we increase the order, the model can bend more throughout the data. The two candidate models I would pick from are a parabola and a 6th order polynomial. And the reason because the parabola has the lowest AIC and the 6th order has the highest R-squared adjusted. But I am picking the 2nd order. Why? Why? Well, think about this. What kind of models are better? What kind of models are better? Models that are easier or models that are more complex? Simple models or complex models are better. Like if I tell you I can draw the relationships in data with a line or a parabola or a 6th order, something like that. It's close to 6th. I think it's a 7th order. Simpler models, right? So what would be your number one choice right here? A line, a parabola, or the 6th order polynomial? Here we go. Ready? 1, 2, 3, 4, 5. That should be about right there. The line, the 6th order, or the parabola. So the line. Simpler is better. But why are we not picking the line? Well, it's obvious right here. We are not picking the line. Why? Look at this. We would not pick the line because there's a what right there. We would not pick the line because there's a what. And I can actually go back to the Kahoot output. We would not pick the line because what? Clearly going from the line to the parabola gets us closer to the real model because there's a jump of a decrease of AIC about 61. Does everyone see that? So there's a huge decrease in AIC right here. That's ridiculous. Also, R-squared adjusted goes way up. So that's really good right there too. Now, these are pretty similar. Look, they're within about 0.006 of each other. Very similar R-squared adjusteds right there, but we do have the lower AIC here. So since this wins on at least one metric, I'm going to go with the 2nd order model. So using the parabola, so here would be my write-up of this one. A choose order was done to look at the polynomial order to put for the variable, the x variable in our model. We saw that the 2nd order had the best AIC, and this indicates to us that probably using the parabolic relationship with this x, or you could say 2nd order relationship if you don't know it's a parabola. The 2nd order relationship would be the best idea. You could then add addendums, so that would probably be 10 out of 10 right there, knowing what this means, knowing AIC is closer to the truth. Who yes or no in the chat. Does this output make sense right now? Tell me what you think. We only got one more question after this, but does this output make sense? Remember, any output from any of the slides, knowing what it means, knowing what it shows you. Awesome. Good stuff right there. Let's do the last question. Here we go. Good job, Bella, right there. And Parker, Wonder Llama, and Mighty Yeti Mirror. Top 3 gift prizes. Last question of the day. Make sure to email me. Which value tells us the model's statistical significance? Pretty easy one here at the end. I'm being nice at the very end of this. Which value tells us the model's statistical significance? Why did I put a minute on this one? So, got some missing. 6 observations deleted due to missingness. The typical miss the model makes. The percent of variation of y explained by x. The adjusted for... Oh, wow. Thank you, everyone. Yep, it is the r squared, or the p-value. I was talking about r squared. The p-value tells us the statistical significance of the model. I forgot to put something on here. The partial f. You should definitely know a partial f. When do we use a partial f? Actually, let's go run one then. Since I didn't put one on here, let's go do a partial f. When do we do a partial f? Will that work? No, it doesn't like it. When do we do a partial f? And then you can tell me if you want to see other output and understand what it means. When do we do a partial f? It's kind of the answer right there. When do we do a partial f? No, what's it mad about? No, it doesn't like that the data command's not on, I don't think. That's why you got to use data. What? What's it mad about? Did I mess it up? Y tilde x, comma, data equals... It's complex not made. When do we do the partial f? Oh, it might be that there's... It's got it right there. Nova, simple, comma, complex. Models were not all fitted using the same data. Oh, it's the missingness. Darn missingness. Darn missingness. Survey 11, save into complete. No. Survey 11, complete cases. No, complete cases on the rows. Run that. There we go. Well, that's interesting. I wouldn't give you this big of an output. Not leverage. Partial F isn't leverage, though. Partial F is not leverage, and the code right here explains what the partial F is used for. Partial F is used when doing what? And what does this mean right here? Especially that. It's the only thing that really matters. Or this kind of matters. That's like the second most, but this is what matters most. Partial F is going to be what? So the code kind of gives away what it's doing, which I did include a lot of the code to show you. Comparing a simple model to a complex, and what is the end result of this? What is the conclusion of this partial F? Yeah. We can do one of those here, Brian. You got it? What is the end result of that? What does that tell us? That is the most important thing to know from this output. Give it a moment. Remember, if you can practice it, it's all the better. So what does the end result of that mean? What does that mean? Thoughts? So we're comparing a simple model to a complex model. Not that the model, because there is a comparison right here between models. So it's not that the complex model is statistically significant. It probably is, but we're comparing two models. Yep, Matthew's got it right there. That the complex model brings new information, like the variables in the complex. When you go from the simple to the complex, the difference between them is statistically significant. That's what it's comparing right here. It's comparing the differences between the two to see if the reduction in sums of squared error, like that's, we probably don't want to go statty on it and go stats language, but the complex model does bring with it variables that bring new information, and that's the p-value right here. The amount of coefficients it brings are the degrees of freedom. The most important thing is this right here. Like that's the most important thing. The F is once again the ratio of what we see explained versus what we would expect via random chance. Most important thing is going to be the p-value. If you don't get the p-value, you miss the most important thing for what the partial F is telling you. Other things are just calculation metrics and differences in the amount of coefficients in the models. To make a logistic model, We go right here and go GLM, and we do something like, yo, we might have something else then. Satisfied with weight. But what we have to do right here, and this is a good thing to show, is satisfied with weight. Why can we not do logistic on it? So why can we currently not do logistic on satisfied with weight? Why can we not do logistic with satisfied with weight? And I'm going to do logistic because I'm going to do something to it. So let's go right here and go to survey 11. Why can we not do logistic? There's that. Yes, I want that. And then what? Did I just do that? Has more than 12 exactly. I thought I overwrote it. If else, survey line satisfied weight equals yes. Oh wait. Wait. It looks like it's. Oh my god. Wait. Did I not just overwrite it? Then why did it? Oh, because it's attached. Oh my gosh. Petrie said don't do attach. Deattach. Petrie's not a fan of attach. That's why. Oh my gosh. Wow. I should listen to Petrie more often. There we go. Petrie is not a fan of attach. Reason being is you could run into errors like I have because I was working with what I attached and attached won't update it. So what I did right there was I recoded the variable so that it only has yes and no in it. So if someone's satisfied with their weight, the answer is yes. If they're not satisfied with their weight, I said no. So now we can do the logistic model right there. So many things you can run into it. I love it personally. The only good part about attach is you get what? Why does Brian like attach? So why do you think I like attach? I'll show you. That's why I like attach right there. Why do you think I like attach? That's why I like it. Sure. I want to do the other one. There we go. That's what do you think I like about it? Which still use your data equals probably. We're showing once again why you want to put data equals. You can technically not use it because of the autofill right there. Great job, Sam. So that's a really awesome part about it. It's so helpful to just like know you didn't mistype a variable. So much easier. Binomial, doesn't matter.
It doesn't matter
which way we write it. You can even do that. I don't like that way though. Error values must be 0, 1s. It looks, oh, I think I know what it's mad about me about. I think the satisfied with weight, I think it still has, let me try this. Drop levels. I think I know what the issue is. I think there's still extra levels on it because, let me try it. And it's still mad. Satisfied with weight. What shouldn't be? Y values must be 0. Error in family initialized binomial. GLM. Is it not? Oh, I think I know the issue. Oh, 10,000 points if you see the issue. I knew it right as I was thinking through it because I've been helping a lot of people. I've been helping a lot of people. Yeah, well, because I've been taught a lot. Then you might know the issue then for 10,000 points. You see it? I got to move my head. I'll fix it once we see it. Like, now you can't see it. Now you can. Can't. Can. I mean, kind of. No, you can't. What's the issue? Look at what I'm trying to block. It's character. Yep. Oh, Mubot. Let's see if Mubot sees that. Hopefully I didn't like break Mubot. Yeah, the fact that it's a character, that's not, no. It goes back to here where I changed it. I should have ran on this, put this inside of a factor right here. Turn this into a factor, run that, and there we go. Now go here and run that. There you go. Fixes it. Right there. So this is the biggest thing, and this is what I was posting about on Discord, is if your data's not properly created, things are going to be huge problems. So that's what I've been mainly working with people on, is like, your data needs to be right. If your data doesn't look correct, problems. So we don't like that. Bad data, bad problems, it makes us go crazy. Drop levels looks like it doesn't need to be used. probably fine right there. There we go. Good to go. Okay, let's go look at this model now. We now have a model, which is good stuff. So now we can do summary of our model. And there it is. Okay. We can actually view it. Okay. What do we got going on right here? We got two S-shaped curves. We're figuring out if people are satisfied with their weight. And what do we notice? And you can kind of see that interesting. Did I include an interaction? I didn't. Wow. That's very interesting. I wonder what happened. Does anyone want to give some Ooh. Look at this. Look at that. Wow. None of the p-values are significant now. And that's what I would think. Or, I mean, from what I've seen, and it speaks, there's a lot to notice right here. And I want you to notice this, which is very interesting. What does this say right here? It's like a societal thing we're critiquing on right now. What does that mean right there? What does that mean? But this is, of course, two individuals. So, and it's not if somebody gets taller. Do not interpret this if somebody gets taller. And we do see the coefficient of height is positive at all points. It would just get more positive for males, which means the males have the steeper slope. So females are almost, yes. If you take two individuals who are female, then people who are female, well, you can look in almost all instances are less likely to be satisfied with their weight than males who are otherwise identical. By otherwise identical, we mean if you take two people of the same height, one is male and one is female, then the female is less likely, and that is seen over here with the male has a negative coefficient. So male has a negative coefficient. Let me go check here. Gender male has a negative coefficient. Oh, that just means they're. Let me double think. Let me think through this. Is the inner? Oh, you know what it is? That's so tricky. Oof, this one's so tough. Gender male has a negative coefficient right here, but because we're at such a high height, this value of the interaction right here is actually making the coefficient of males taller because we're only looking at height 50, and then the slope, it's basically overcoming it actually, and that's why after 50, males are higher than females. So what you're looking at, and we could probably figure out, that might be, wow, I never realized this. This value right here, if you divide it by this actually looks to be where the exchange happens, where it changes. So that's where males start to have a higher values than females, and that is pretty much all not reasonable, but the majority of heights we see would be contained in this range in here if you were to make a normal distribution of heights over this. Nothing wrong with being below or above here, but that's sort of outside the range of what we normally see. Normal meaning most common towards here. Like even if you're over here, you're less common, and down here, you're less common. The normalcy isn't there. So normal doesn't mean bad, it just means most common in this instance. And so with this right here, the interpretation right here would be what for height? So just give the height interpretation. Give the height interpretation. Give the height interpretation. Two people who are otherwise identical, what? Good stuff. We're asking about interpretations of multiple logistic. So what would it be? Two people who are otherwise identical, but one of them is taller. What? And it's shown over here in the graphic. What would we say? Got about 10 more minutes. I'm going to eat a little and get ready for 201. Two people who are otherwise identical, but one is taller than the other. The person who is taller is what? More likely to be satisfied with their weight. Do not mention this value because it's not a unit difference. It's not a 1 unit difference. Then we see right here, and this is weird, be careful, two people who are otherwise identical, but one is male, and then we only have female right there. So one is male and the other is female. The person who is male is less likely to be. You might add an addendum that we do need to consider that there is an interaction on these two variables, such that the coefficient of gender male is most likely positive for most of the heights we see, where the person who is male is actually more likely. The graphic kind of shows that because of the interaction right here. If we don't have the interaction, then you'll see the positive coefficient on the male has the male S sigmoidal curve always above the female sigmoidal curve. And that's because it's a constant relationship right here, where two people who are otherwise identical, but one person is male and the other person is female. The person who is male is more likely to be satisfied with their weight. And it's very interesting. And then last but not least, we could go here and get a confusion matrix for this and look at it. And it does all right. Well, does it really? Does it? The misclassification, or let's go for the accuracy of the model. The accuracy of the model is, there's the accuracy 60%, which is not amazing. So 60% of people are 59.5, 60-ish percent are classified correctly. And then the naive model classifies 55. So really, when you think about this, the model's not doing that much better than the naive. And that's what I would talk about, to say like 60% are classified correctly using this model versus 55% are not classified correctly. It's fair to say that, you know, about half the people are not satisfied with their weight. You can see it right here. And 55% are not satisfied with their weight. And this model really doesn't help us figure out who's satisfied with their weight. I'm sure we could do other things. And here's where we could. Mubot's just talking away to himself right here. Watch this. Let's go and make a much bigger model. And go here to full. And this is what you could do for your final. So here we go. And then let's go S, save into step. I don't do it with logistic that much. M is the naive. Well, it's not the naive. It's the starting point, though. List equals lower equals M, comma, upper equals full. I'm going to capitalize full. And good job, Hayden and Bella. Direction. I think there might be something additional that I need to do for this forward. Let's see if it works. Well, it's mad. Did I miss a comma? Put a period. Wait, what's it made about? Unexpected comma. What did I mess up? Unexpected. Oh, wait. Lower. I just wrote these out earlier. List equals. Oh, wait. How did I mess up the step? Step equals, list equals. It says unexpected comma. What? Oh. Who sees the error? Step M, list equals lower, equals M, upper equals full. Did I misspell lower? 2 seconds right here. Where's the model building notes? Even I gotta check things every once in a while. Model building RMD. Where is it? Let's see. Who has thoughts? Get this loaded up right here. BS 320. I'm like, what did I do wrong? Model building. Model building. Okay. Okay, here we go. And let's take a look. Where's step procedure? Step, naive. Oh. Scope equals list. So scope equals list. There we go. Scope equals list. And now we've built a model right here. We did variable selection. And now our model is much bigger. Well, we saved it into S for the step model. Scope equals list. And we don't have that many more variables. many variables do we have? There we go. Political beliefs. Interesting. These are the variables: attractive, weight, height, all these things right here. Now we can look at the confusion matrix, which we should get a much better predictive model. And oh, I did the, there we go. Not that much better though. If you look at lowered this, so really satisfied with weight looks to be a hard variable to predict. What we could do is we could do this in both directions right here. And now, there it goes. And actually did it that quick. There's the model ending off now. Smoker, interesting. And so that didn't visualize the model. And then let's do confusion matrix. And, well, not that awesome of a model. Doesn't do that well. With that, any other last questions? Knowing your output is key right here. Good work. And if you, oh, we didn't even go to the end to see who won the Kahoot. Holy mackerel. Sorry. Oh my gosh. In third place, Fabulous Emu. In second place, Wonder Llama. Please email me everyone who won. And in first place, whoa, that was super close. Mighty Yeti. Sorry, I got so, we were talking over output that I was like, wait a minute. So great job there, everybody. Make sure to know your output. It's all about the output. It's all about the interpretations. Review the slides, review the notes, know how to read the output, know what it means, know how to explain it. You're welcome, Matthew. I was like, how did we not even see team up for a rematch in tallest tower? What is this? New mode. I'm just gonna see what this is. What is this? Get ready with your team to build it. You're welcome, Bella. You're welcome, Olivia. What? You're welcome, Emma. I'm just seeing what this is right now. This might be something fun to do in the future. Was it literally gonna like... See if anyone's doing it. Do I not get to see what it is while you're doing it? Oh. Wonder Llama, nice. It's giving you questions. And then you just build the towers. Interesting. Do you think this would be pretty fun? Monster incoming. What does this even mean? See, this is interesting. Like, I'd have to like announce this as I'm doing it. I'm like, oh my gosh, the ocean team is doing great, but a monster's incoming. The problem is like the educational aspect of me doing this. So can you not build right there? It looks like. This is this is interesting. See, it's not good for announcing. I wonder if there's other modes too. Well, I'd have to wait another 3 minutes and 20 seconds for this to end. It's just not good for announcing. Oh shit, I like it. It's just building that one tower up right there. Yeah, it's... I don't think I can... I don't know. What are your... Sam, are you the one playing it? Your thoughts on this? I mean, if I had like 100 questions, it might be pretty fun. I could see how like... We just need more questions. And maybe it'd be pretty fun. Oh, we got over there Mighty Yeti playing too. Oh, so what happens when you build past the monster, I'm wondering? So is it just showing you the same questions I had in the Kahoot, like the 17 questions, but maybe recycling them, like going a random set of the 17 questions? See, here, I'll join in. I got someone's team. I want to see it here too. Half the time's done? Okay. I'm joining in. Game pin. It's probably gonna put me on. Oh, look at that. The monster got them. Watch me be on their team. amount. I'm on ocean. Oh, and it's... Oh, that's interesting. I'm messing up your design. I mean, how many do you... Oh, and then you gotta do like a tap thing if you miss it. That's interesting. Show you tells us statistical significance. Oh. Oh, and then it times you out. How do we interpret probability? This is kind of neat. I kind of like this. Well, you gotta get 2 questions right to get the next level. Like, interesting. What do VIFs indicate? Interesting. We'll finish this. Oh, that small output's really bad. Oh my god. It's a crane game. I don't know. Oh god. Oh, oh, that's so weird. Oh my god. What does the following show? Oh, you can't even see that output. You can't even see that. Interesting. You're welcome, Courtney. This is interesting to check out right here. It's kind of neat. You'd have to redesign the questions. Oh, man. Nice job over there. Yeah, good job building that up. You beat us by 1 story. Good. Mighty Yeti did that all themselves. Great job, Mighty Yeti, right there. I might have been. I don't know which one of those I was over there. Oh, I was Rockstar Raven. So, yeah, you did it. Nice job. Wow, you got a lot right there. Okay, well, that's got it. That's Browse Cahoots. I'll check that out. Till next time. Bye for now, everyone. Bye.